heavy metals.
Thank you. So first I would like to thank the organizers for the invitation and the opportunity to give you a review of our recent talk, or our recent work. So this work deviates a little bit from the theme of this conference on antiferromagnet, but nevertheless is quite interesting. So the outline of my talk, first I will discuss this novel approach to generate spin currents from acoustic phonons via spin-orbit interactions in heavy metals. And I'd like to acknowledge the postdoctoral fellow, Farzad Mahouzi, that has done all the work. He has developed a wide range of codes from spin-orbit torque to Gilbert damping to phonon-induced spin Hall effect. And then at the end of my talk, I will flash one slide on sublattice Jablonski-Marie interactions in PT symmetric antiferromagnets with broken local symmetry. And I'm looking forward to discuss this topic more in this conference. So one of the main objectives of spintronics, of course, is the effective conversion of charge to spin currents. And there are various approaches for generating spin currents. The most traditional is the current-induced box spin Hall effect, where basically the efficiency on converting the charge current to the spin current is given by the spin Hall angle. And the spin current is proportional to the spin Hall conductivity divided by the charge longitudinal conductivity. And I would like to mention, of course, because for comparison later, the spin Hall conductivity, the intrinsic spin Hall conductivity is an intrinsic property of the material, which depends on its band structure. Whereas the longitudinal conductivity, depends on the relaxation time and the scattering. Now, other approaches which do not invoke the spin-orbit coupling are basically magnetization precession, spin pumping, the spin-Seebeck effect, laser-induced demagnetization, and the current-induced spin polarization effect in magnetic tunneling junctions. However, more recently, there have been experiments which they have demonstrated a new approach of generating spin currents. So I'd like to spend the next few slides to overview the experimental results. So the experimental setup consists of a heterostructure consisting of a substrate, which is a piezoelectric lithium niobate, and heavy metal, which is either tungsten, palladium, tantalum, or copper, cobalt iron, MgO, and tantalum. So the whole bar is placed between two interdigital transducers, which are connected to a vector analyzer, which excites surface acoustic modes between the two transducers. So of course the acoustic waves can go from this to that or vice versa. So the typical transmission for the tungsten heterostructure as a function of frequency is shown in this panel, where as you can see the transmission becomes maximum around 194 megahertz, which turns out to be the fundamental excitation frequency of the standing of the surface acoustic wave, which depends on the dimensions of the two transducers and also on the velocity of the substrate. So I forgot to mention that the cobalt iron is in plane, has an in-plane magnetic anisotropy, and experimentally they apply a magnetic field in plane, which forms an angle phi with respect to the propagation of the acoustic surface wave, which is along x. So what they measured is both the longitudinal Hall voltage and transverse, and what they analyzed mostly the results in terms of the longitudinal voltage. So in order to remove the, in order to find what is induced by the sound wave, they had to subtract the voltage which is off resonance. Namely, if you go off resonance from the fundamental excitation, you remove the corresponding voltage. So this voltage is basically the voltage induced by the acoustic waves. So what is shown here is in the 4 panels is the voltage as a function of the angle phi for tungsten, platinum, and copper, and then I'll come back to this. So for all these 3 panels, the acoustic wave is propagating from terminal 2 to terminal 1. So first of all, note that the sign of the 2 signals for tungsten and platinum are, the sign is similar, even though the spin Hall conductivity for platinum and tungsten have opposite sign. The interesting thing is also, of course, when you have copper, and copper has very small spin-orbit coupling, the signal is negligible small. Now, the other thing is if they reverse the direction of the standing acoustic wave, instead of going from 2 to 1, if the acoustic wave goes from 1 to 2, note that there's a reversal of the sign of the voltage, but also the offset has reversed its sign. So they were able to fit their data by this expression, where this is independent of the angle, and this is the charge pumping due to the acoustic wave. And the question is, of course, there is a sine squared 2 phi dependence, and the question is, what is the origin of this coefficient? So what they did is they took the ratio of this coefficient divided by this, which is this term, and what they're showing is the normalized coefficient as a function of the thickness of the heavy metal for the case of tungsten. So note basically that there's a maximum as a function of thickness, and they did independent spin Hall magnetoresistor measurements as a function of the angle of the ferromagnet in plane angle, which is shown independently here. So this is the normalized spin Hall magnetoresistance as a function, again, of the thickness of the heavy metal. So as expected, of course, there's a non-monotonic increase, there's a maximum, and the maximum is related to the square of the spin Hall angle, and according to the spin diffusion model, and where the thickness where this reaches its maximum value is the spin diffusion length. So these 2 curves suggest that the origin of this is associated with spin current induced in the non-magnetic metal by the surface acoustic waves. Note, however, there are some differences between this and that. First, the spin Hall magnetoresistance, the angular dependence is not sine squared 2 phi, it's just cosine of 2 phi. So you know the period here is 90 degrees. And the other thing to note is that the percentage here and here is quite different. So there is an order of magnitude percentage increase for the surface acoustic induced spin Hall due to acoustic waves. And finally, they found that it depends linearly on sun acoustic wave frequency and the power. So they suggested a couple of mechanisms, phenomenological mechanisms. The one is that there's a dynamic change in Berry curvature due to the electron wave function, which is induced by the time-dependent lattice displacement, which is associated with the wave. The second mechanism that they proposed is sort of like Rashba term, where basically your interaction Hamiltonian involves the U, which is the atomic displacement of your atoms. And it turns out that if you use this expression, basically you can get that the spin current, whose polarization is along Y, is proportional to the derivative of the atomic displacement with time. So the objective of our work was to try to understand the mechanism for phonon-induced spin Hall effect. But before I go there, I'd like to bring to your attention a paper seminal by Kioussis in the 1980s, on the adiabatic electron pumping. So he considered a one-dimensional spinless electron gas in one dimension, which is moving in a periodic potential, U of x. And if one gives a velocity to the potential, so the potential now becomes time-dependent, basically within one cycle, one of the potential minima moves within a cycle by a distance a, which is the periodicity of the potential. And if the electrons follow adiabatically the movement of the potential, basically that can induce a current, and the current induced basically induces a charge, which ends up being an integer, which is the occupation is the number of electrons per unit cell. And experimental demonstration of the adiabatic electron pumping in semiconductors, for example, in nanotubes and also quantum dots, was demonstrated using surface acoustic waves way back, which basically they make the potential time dependent. So the question that we wanted to address in the next 2 or 3 slides, I'd like to present the theoretical formalism, which is a little bit different, is ab initio based, but is different than the typical ab initio based codes that you have in VASP or. So what we consider is a strain. So we consider a time-dependent and spatially dependent strain, in this simple case along x, which is shown schematically here, which is propagating along the x direction with a vector q and frequency omega. And under this time-dependent, spatial-dependent strain, one can write the Hamiltonian. H0 is strain-independent Hamiltonian, and then basically ij here referred to the x, y, z coordinates. And hij is basically the derivative of the Hamiltonian with respect to strain in the limit of the strain going to 0. So this is the deformation Hamiltonian, and which is multiplied in the linear response with the external applied strain. So one can remove the time dependence of the system by applying a gauged transformation. And this gauged transformation basically increases the Hilbert space of the electrons by including the phonon degrees of freedom. And this is referred to as Floquet space, which includes the phononic degrees of freedom. So that is shown schematically on the figure on the right. So each level here is associated with n number of phonons. So one has an auxiliary direction, which is the chemical potential, which is the electronic chemical potential plus the number of phonons on each energy on each level. So the phonon is shown with this wiggle curve moving from right to left. And the phonon, of course, let's say gets absorbed by an electron, and then basically that means that you have one phonon less in your system. So the electron jumps, undergoes a transition from this level to this level, where the number of phonons has decreased by 1. Of course, the coupling between this phonon levels is induced by this strain electron coupling, which there are more details how to derive that. And of course, the spacing between these levels is just h bar omega, where omega is the phonon frequency. Okay, so the next thing is I'd like to discuss is a little bit how do you calculate the charge and the spin current. And of course, in the ballistic regime and in the linear frequency response, you can write the non-equilibrium density as 2 terms. So the first term is the Fermi C, so it's basically an integral over all occupied states. And the second term is basically the Fermi surface. So note these are the Green's functions which are evaluated at the Fermi level. And omega is a matrix for the phonon matrix, which is diagonal and depends on how many levels of phonons I showed in the previous slide you include. So basically, there's a cutoff of the number of phonons, and one has to check the convergence with the number of phonons included. The Green's functions, of course, they are inversely proportional to the Hamiltonian, and of course, they value at the Fermi level, and this parameter is important, so this is referred to the broadening parameter, which is inversely proportional to the relaxation time. So having calculated this density matrix, one can go and calculate the charge current, which is the trace of the derivative of the Hamiltonian with momentum and times the density matrix, and similarly, the spin current, which is the trace of the Pauli matrix times the derivative of the Hamiltonian times the density matrix. Okay, so I think now this is important in terms, sorry? No. Okay, so, sorry. Okay, so the question is how does your system changes when your eta parameter, your broadening changes sign. So one can actually break the even and odd components of the density matrix to the even part and the odd part. And it turns out after some calculations that the even part is constant, and that includes both the Fermi surface and the Fermi sea. And what I'll show you in a minute is this is associated with a Berry character, which is very different than the current-induced or electric field-induced spin Hall effect. On the other hand, the odd component, basically it's only, which is only coming from the surface C, it turns out to be only the ohmic component, which is again, the ohmic character, which is different than what is in current-induced. So it turns out that one can derive, in the limit of eta, the parameter eta going to 0, one can derive an exact formula for the current density, which is basically typical Berry curvature, where these derivatives are just given by the Hamiltonian matrix elements. Okay, so this table is important. So what is shown here is the even and odd components of the charge current, which is the first row, the x, y, and z components, and the odd components. And similarly, the even and odd components of the spin current density for different spin polarizations. So what is shown here is all, for the current, everything is 0, except for the even part. And the even part is only the x component, which means that the current is moving along the direction of the propagation of the phonon. If you look at the spin current density, all the even part are 0, and the non-even part, which is coming from the odd, and this is related to the spin current, which is where the phonon propagates along x. The spin propagation is along z with spin polarization along y. And of course, it's symmetric. So in contrast to the electric field, where the ohmic currents are odd or even functions, basically this is quite different. So I'll show you some results now in terms of the charge current and the spin current on the two vertical scales as a function of the wave vector. What we find is that both of them vary linearly with q. And in order to look at the sensitivity of converting charge to spin, what is shown here is you take the slope of these two curves, and we have plotted them as a function of the strain amplitude square. And you can see here on the vertical side is the current, is the current, and this is the spin current. And both of them, they are, for at least small strains, they vary quadratically with a strain. So one can fit those ab initio results with this expression, where the charge current is proportional to q along the direction of q and is proportional to the square of the strain, whereas the spin current is a cross product of the spin polarization cross q and quadratic in terms of the strain. And we have calculated all the various components of the elasto-dynamic charge and spin conductivity for different types of strains. How many more minutes? 5. Okay, I have only 2 slides. So, we have, in order to understand the dependence on the broadening parameter of both the charge and the spin current, What we're plotting here is the longitudinal elasto-dynamic charge conductivity, which is this coefficient, as a function of the broadening, for where the red is only the Fermi surface and the blue is the total contribution. And as you go to the diffusive regime, when eta becomes large, basically there's a discrepancy between these two because the total current density is calculated in the limit of eta going to 0. Similarly here, what we show is the coefficient of the spin Hall conductivity as a function of the broadening for a different number of phonons. And as you can see, for large eta, this goes inversely proportional to eta. But for small eta, actually, there is a hump, indicating that as you go to the ballistic regime, basically you need a larger number of phonons in order to converge your results. So the next slide, the next graph shows the dependence of this coefficient and this coefficient as a function of the spin-orbit coupling to see what is the effect of the spin-orbit coupling as the spin-orbit coupling changes from 0 to 1. So note for the longitudinal charge conductivity basically is quadratic, indicating that the modulation of the band structure, this is a non-magnetic material, so the eigenvalues, the change of the eigenvalues are proportional to the spin-orbit coupling square. Whereas for the spin Hall conductivity, of course, for zero spin orbit coupling, basically it vanishes, indicating that this term actually is, the spin Hall coupling is responsible. Okay, so I'll just flash on that in terms of the mechanism. So what is shown here is the two coefficients I showed you as a function of the chemical potential. So the green curve applies to the charge conductivity, and the black curve applies to the spin conductivity. And note that both of them correlate very well, which is surprisingly. And they change sign. As you cross the Fermi level, basically they become positive on when the chemical potential is above 0, and they become both negative when the chemical potential are below 0. And it turns out these two curves correlate well with the derivative of the density of states at the Fermi level, which is plotted with this red curve. So what this red curve shows is basically, if you look at this curve, there is a qualitative correlation with the derivative of the density of states, Okay, so finally, in order to compare with experiments, one could write down an expression for the charge current in terms of an effective elasto-dynamic conductivity, which is proportional to Q and omega and times the square of the strain. So taking from experiments, basically the values of the current density, the frequencies, and the wavelength, which gives you Q, you can actually calculate, and for a typical strain, let's say of 0.01%, you get this coefficient for the charge conductivity, which is around 10 to the 12 in these units. And as you can see, basically, roughly speaking, when you look at the longitudinal charge conductivity as a function of broadening, if you go to the ballistic regime, basically this range is about 10 to the 11, 10 to the 12, which is roughly speaking in approximate good agreement, qualitative agreement with experiments. And with that, I'll close. I think I'm on time? Okay. I'll close this, and this is a summary of our results. Thank you.
Thank you very much. So the talk is now open for questions. Yeah, Helen in the back. I'll give you the mic. I'll give you the mic.